Project 3 and the pink sheet, which is an addendum. So make sure you got the pink sheet along with Project 3. So if you didn't pick up the pink sheet, just pick it up on your way out. Today and Friday, we'll be covering transformations of functions, and we'll see what happens on Monday. Don't forget, one of my classes, I don't know if it was this class or my 840, told me that even though I thought our next quiz was Friday, everyone convinced me that it said Monday on their syllabus. So I've been saying our next quiz is Monday. And I said, please show me this schedule because I can't find it anywhere. And it is scheduled for Friday, but because I said I would move it to Monday, let's move it to Monday. So that quiz will be on classes 14, 15, and 16. And this is all the linear equation stuff. It's slopes and finding equations for lines and linear regression. That's 14, 15, and 16. So I think that's quiz 5, if I'm right. I think it's 5. Now, you usually know this stuff, Adam. Quiz number 5 on Monday. Okay. So let's take a look at today's notes. I did have some notes for today, and I think I left it in the studio. Okay. I'll be right back. Got my keys and notes. Yep. Yep. Okay, so if you take out your pink sheet for a minute. Okay, if you take out your pink sheet. Okay, so in your project, as you read through your project number 3, it refers to something called parent functions. And parent functions is just another name for common functions. They're used a lot. And you should have a good sense of what parent functions are in your mind before you even think about graphing them. You shouldn't even have to graph them, really. So what do we refer to as parent functions? On this pink sheet, you'll see 6 common functions. And these are what we refer to throughout Project 3 as your parent functions. The first one's just a straight line. It's called the identity function because if x is 1, y is 1. If x is 2, y is 2. If x is -3, y is -3. It's just your line with slope 1 right through the origin. Then the next one is your baby parabola x squared before anything's done to it, right? It's just your basic parabola. 3 is your absolute value function, which looks like a big V. 4 is what we learned in class a few weeks ago called the greatest integer function. If you were actually trying to graph this in GeoGebra, you would put in floor, F-L-O-O-R with the X after it. So you might want to write that down. Square root function, okay, is only defined from 0 to infinity because you can't take the square root of a negative number. So the domain of the positive square root of x is 0 to infinity, including 0. Then your reciprocal function. So those are the 6 parent functions for your project. In today's class, we're going to be starting our discussion of transformation of functions, which is if we take a basic graph, one of our basic parent graphs, and if you notice the first 3 functions here, j of x is your parabola, g of x is your square root function, h of x is your absolute value, and those are the same parent functions we have for our project. We've thrown in a step function for you. This is not considered a parent function because this particular function isn't common per se, but for our explorations on transformation of functions, we're going to call this a parent function as well. So today we're going to be working on these things, and we're going to be manipulating them and adding things to them and multiplying these functions by things and seeing how does it affect the graph of the function? What happens to the basic graph of each of these functions when I start adding and subtracting, multiplying and dividing these things? So let's take a look at the first problem, which is called a vertical shift. Okay, so what this means is something's going to be happening to our function, our original function, And the thing that happens is going to be happening in the vertical direction, which means up or down. Okay, so up or down. So our function's going to be moving somehow up or down. So here's j of x. J of x is equal to x squared. What would this equal? J of x plus 3. What would that look like? What would that equation look like? X squared plus 3, because you simply replace j of x with what it's equal to. Okay. So I have this function. If you want, you could use new function notation. If you want, you could say this is going to be called p of x. P of x is x squared plus 3, if you just wanted to give it a new name. Okay, so notice whatever goes in for x, it's still being squared. I'm still performing my original function. Then I'm going to add 3 to the x squared term. All right, so y equals x squared plus 3. Changing the equation from x squared to x squared plus 3, because that's what this means. Y equals j of x is y equals x squared, to x squared plus 3. Am I changing the outside of my parent function or the inside? Do you have a sense of that language? What am I doing? So y here, this is y equals x squared, and this is y equals x squared plus 3. Am I making a change outside of my original function or inside? And outside. And what when you say outside, how do you feel that outside? What do you, for those people who said outside? It doesn't change my original function. X, my original x is still being squared, but then after I square it, I'm adding something to it. So it's I'm outside the function. I'm operating outside the function. Okay? Outside. That is, we are changing the outputs or our y values. That's the only thing changing. The outputs are the y values of our parent function. So how have these outputs changed? Well, let's see. Here's our original function, x. Let's pick some numbers, -3, -2, -1, 0, 1, 2, 3. That's my original x. J of x says to square it. Square everything. So let's square everything. We get 9, 4, 1, 0, 1, 4, 9. So my points on my graph, if I were to graph it, would look like this. Just your standard x squared parabola. Okay. So we all know what that looks like. Okay. And if I called it up, it's not that one, it's not that one, not that one. There we go. So there's j of x. And notice j of x is my original function. My new function I'm going to call j sub 1. That's my offspring. Those are my kids. Okay, here are the parents, and now we're going to start getting some variations of the parent function, the offspring, okay, the transformed function. So notice when c is 0, when I add nothing to this, I have the same function, so the picture is exactly the same. All right, so let's see. What have we done to x squared? We've added 3 to it. So over here, so we're keeping all of our x values the same. These are all the same. And now I'm changing my output. My output now is x squared plus 3. So I take my x, I square it, and I add 3. So I get 9 plus 3 or 12. -2 squared is 4 plus 3 or 7. -1 squared is 1. 1 plus 3 is 4. 0 squared is 0 plus 3 is 3. 1 squared is 1 plus 3 is 4. 4 plus 3 is 7. And 9 plus 3 is 12. So what if I were to graph this, what would my ordered pairs look like? Well, they would be all of my original x values. So -3, -2, -1, 0, 1, 2, and 3. And what did we say happened to all of our y values or our output? What happened to all of our output values when we compare 9 to 12, 4 to 7, 1 to 4? What's happened to our outputs? I've added 3 to all of them, right? So now I get 12, 7, 4, 3, 4, 7, and 12. So before today's class, if we wanted to graph a new function, we have to go through this plotting point stuff. Okay, but after today, once you know the basic shape of your original or your parent function, you're going to learn stuff today to immediately draw the new function without having to plot points. You might pick a couple of points and what we call key points of your original graph, make the changes that your transformation calls for, and then sketch your other graph real quick like that. So we're going to try to start doing away with creating graphs this way. So how have the outputs of our parent function changed? We've added 3 units to all outputs, or our y values have increased by 3. Okay, that's what's happened to them. Does that make sense to you? So you see that everything's had 3 added to it? All right, so in GeoGebra, let's take a look at our parent function, j of x, and our new offspring, which is still, we're keeping our original function, j of x, and we're adding 3. We're going to graph them on the same set of axes, and then we're going to see how the 2 graphs compare to each other. Okay, so I don't remember which graph it was. Was this it? Okay, so what's our value of c? What are we adding to x squared? 3. So let's move this c value. This is called a slider, and if you want to get a slider, it's found in one of these windows. You can find it if you look for it. So let's go to 3. Boom, boom, boom. There we go. So there's 3. There's our new function. So if you were looking at these 2 functions, has the shape of your original function changed at all? No. What's the only thing that's happened to that black function? It's shifted up by 3 units. Everything, so if you picked a couple of key points on this original, right, on this original function, so if you pick those original points, and even if you put little like labels on them, okay, -1, 1, negative, what we just did in our original table, and then you found the new points, you can now see that instead of 0, 0, you are now 0, 3. So your y value has increased by 3. And if you go to 1, 1 is now at 4. Okay? And -1 is at 4. So everything has shifted up 3 units. So x squared plus 3, if we go back to our how are the 2 graphs related to each other, you can say the graph of j of x has been vertically, you always got to say which direction, vertically moved up 3 units. The graph of j of x has been vertically moved up 3 units. So now we can fill in the circle and fill in the sentence here. The graph of y equals j of x plus 3 represents a, what do I circle? Vertical shift of the graph, y equals j of x, up, down, left to right, up by 3 units. Okay. So now the question becomes, what happens when I change this value of c here, when this becomes +2 +4 -2 -3? What happens when I change this value of c? What happens to my graph? Okay, so this is where we're going to use our slider tool in GeoGebra to find out. So let's go back to our graph and let's play around with our slider. So let's suppose c becomes 5. See, now this whole thing is moved up 5 units. If c is 4, it's moved up 4, 3, 2, 1, 0. It's back to being the parent function. And then when c is -1, we shift down. We move down 1 unit. -2, we move down 2 units. -3, -4, -5. Okay, so, oops, I guess I can't quite do that. So that the slider on GeoGebra allows you to investigate the different values of that constant that you're adding. and then you can know what happens to your graph. So this is now like the type of thing you're going to add to your cheat sheet for your quizzes and your tests, because this is our first general statement. Can someone fill this in for me? Read it and fill it in as you go along. Nobody can do that in the whole class?
The graph of y equals j of x plus c represents a vertical horizontal shift.
Wait a minute, which one? Can't be both. Well,
I've positive, I guess. Oh no, it's definitely vertical.
Definitely vertical. Why did you change your mind to say definitely vertical instead of positive?
Because I was thinking of the units.
Okay, okay.
But vertical shift by the graph y equals j of x by c.
C units, yep, whatever C is.
The shift is positive. C is greater than 0.
Oh.
Or
Up, okay. If C is positive, yep.
And down.
If C is negative. Okay, good. Okay, so anytime you see a constant being added or subtracted from outside your function, it's a vertical shift. Boom, you got the vertical shift, yes? All right. Very intuitive. You add something, it moves up. You subtract something, it moves down. All right? Let's take a look at horizontal shifts. All right, so which function are we acting on now? Which one, what's our parent function here? Absolute value. So our parent function here, h of x, says whatever you put into my function, whatever you put in, take my absolute value. So it's h of whatever your input is becomes the absolute value of whatever your input is. Okay, so here's my transformation. My transformation says take the absolute value of what goes into my absolute value function. What's my input? X plus 3. So this is going to look like the absolute value of x plus 3. So changing my function from h of x, which is the absolute value of x, to h of x plus 3. So my function's changed from this to y equals the absolute value of x plus 3. Have I acted outside the function or inside the function? Inside. I've changed my input. Okay? So I've acted inside my function. Therefore, I am changing my inputs. Changing my inputs. X has changed. My x values changed from x to x plus 3. So how are the inputs of the outputs? How are the inputs of the parent function changing? This is a tough question. How have the inputs changing? Well, the inputs have had whatever x originally was, what's happened to them now? My inputs have become what? Here's my original input, here's my new input. What's happened to my inputs? Well, it's not absolute value, it's just my input's been increased by 3. That's all. Okay? So my input's been increased by 3, so how's that going to change my graph? So make a guess of what you think is going to happen to the absolute value. Where is it? There it is. So here's my offspring right here, h sub 1, and right now it looks identical to the parent because c is 0. When I change that c to a 3, so it's going to become the absolute value of x plus 3. On your papers right now, just do a quick rendition on your paper of the absolute value graph, just over on the side there, and make a guess as to what you think is going to happen when I graph the absolute value of x plus 3. Nobody's going to look. I'm going to stay right here, and you can hide it from your neighbors. Nobody's going to judge you. Just make a quick guess as what the absolute value of x plus 3 looks like. So remember, we're changing the inputs, so we're not expecting a vertical shift. We should be expecting a horizontal shift. We only have two directions. We're either going to pick this thing up and move it over to negative 3, 0 and start our absolute value, or we're going to move it over to 3, 0. There's only two choices you have. Move it to the left or to the right. So let's see what happens when c is equal to 3. Ready? So what I've heard is, I had a feeling, oh, it's wrong. Okay. So what happened to this? How did our new function change from our original function? How did it shift? How did it shift? To the left 3. So let's write that down. So when we've graphed these on the same set of axes, the graph of h of x, the graph of h of x shifted to the left 3 units. Intuitive? No, totally counterintuitive. When you see a plus 3, you think about things moving to the right. Totally unintuitive. Okay? So here's a couple of ways I can think to try to explain it to you. It's kind of one of those hard things to explain. One way of thinking about this is when you compare x plus 3 to x. You say to yourself, what would you have to do to x plus 3 to get back to x? What could you do to x plus 3 to get back to x? You would have to subtract 3, yes? So subtracting 3 makes a little more sense. So look at here. Here's my original points are going to be in black. Here's 0, 0. Once I become x plus 3, to get back to 0, a y value of 0, to stay at the same height above my x-axis, my x value has to be 3 smaller than my original x value. Why? Because I'm adding 3 to it. So in order to become 0 as my output, my input now has to be 3 units smaller, because negative 3 plus 3 brings me back to 0, and that absolute value of 0 is 0. Let's try it for another point. When I was 2, when I was the number 2, my absolute value was 2. Now, what does my x value have to be in order to be at positive 2? To keep my height exactly the same, I have to be 3 units smaller than this. I have to be at negative 1. Why? Because negative 1 plus 3 is 2, and the absolute value of 2 is 2. Okay, so at negative 2. Similarly, where else was I a 2? Well, when I was negative 2, I was also 2. So on my new function, to get back to 2, I have to take 3 away from negative 2. I have to move to the left 3, because I'm adding 3 to negative 5. Negative 5, when I put it in here, becomes negative 5 plus 3, which is negative 2. The absolute value of negative 2 is positive 2. So this is totally counterintuitive. If you were originally absolute value of x and you add 3 to everything, that means everything's becoming 3 graded. So to stay right at the same y values, your x values have to be 3 units smaller to the left. Okay. The only other way I thought of explaining this, other than just doing this, is when you look at distance on a number line, distance is always a subtraction problem, right? So if you have this, how could you write this as a subtraction problem? X plus 3 becomes what as a subtraction problem? X minus negative 3. So there you see the shift to the left. 3 units. That's another way to see it. So if you change everything to a subtraction problem, and if you're subtracting a negative number, which shifts it to the left, it becomes a plus. Okay? So what's this going to look like now? What will that function look like? X take away 3. Now I have a subtraction. What kind of number am I subtracting? Positive 3. So what's going to happen to my original absolute value function? How many units? Okay. Okay. X take away 3. So in this form of X plus C, when C is negative, it becomes X plus a negative 3, which is X take away 3, and that moves to the right. So it's totally counterintuitive. Okay. So let's come back here and fill in the rest of our little cheat sheet. The graph of y equals h of x plus 3 represents a horizontal, because you're messing around with the input, a horizontal shift of the graph h of x to the left by 3 units. Okay. So that's how h of x plus 3 is transforming h of x. Okay, so now let's see the general case, and this is your cheat sheet information, so you're going to cut all these out to make your cheat sheet. Okay, so here we go. Here's a general statement. H of x plus c. Now remember, this could be any function. In this particular case, we're looking at absolute value, but any function where we're messing up the input here, we're changing the input by adding c, it's going to represent some type of horizontal shift. Anytime you act on the input inside your function, is always horizontal, of your original function, whatever it is, by 3 units, c units, excuse me. So we're going to horizontally shift left or right c units. If c is a positive number, h plus c is a shift to the left. If c is a negative number, h plus a negative c, or x plus a negative c, or x minus c is a shift to the right. Okay, so this is counterintuitive. So what I want you to do now is I want you to skip to your activity sheet real quick. Here we go. And I'd like you to do A, B, and C. See if you can match the graph below. Put A, B, or C on the appropriate graph. And then below it say horizontal or vertical shift, up, down, left, right, and how many units. So then write in what the actual transformation is. So label each graph with the appropriate letter, and then describe the transformation in words. And when you think you have that done, you can call me over, and once one person on the table has it correct, then you can use each other as little answer keys, okay? The first transformation says we're acting on the outside of our function f of x. Here's f of x. We're acting on the outside, so we're expecting a vertical shift. Since it's positive, it's totally intuitive with vertical transformations. So every single one of these points is going to move up 2 units. So that can be found right here. This is A. So this is a vertical shift up 2 units. Okay. Next one, now I'm acting inside the function. We call the inside the argument. We're inside the function. We're adding 2. To get back to x, this is how a lot of people do this in their head. If I want to get back to x, I'd have to subtract 2. That means 2 smaller. So I'm looking for a function where every single point has moved to the left 2 units. So now instead of being at 0, -2, I'm going to be at -2, -2. And instead of being at -2, 0, I'm going to be at -4, 0. What you should do if you haven't already done this, is you take a couple of key points on your graph, a couple of them. Just pick a couple of key points and move those points in whatever direction, up or down, right or left, that you're supposed to. So I'm looking now for -4, 0. I'm looking for -5, 1. I'm looking for 1, 1. So I'm going to look for that along here. And where do I find it? I don't find it anywhere here. This one has been shifted to the left. So this is B. I have shifted. It's a horizontal shift left 2 units. And it probably wouldn't hurt, as long as you guys are getting used to this, to actually label each one of these: y equals f of x plus 2, y equals f of x, then add 2, just to kind of reinforce this new material. And now finally, I'm working inside. I'm looking for another horizontal shift, but this time I'm going right 2 units. So I'm looking for where this graph goes to the right. So now instead of -2, 0, -2, I'm 2, -2. Everything here has shifted to the right. Here's C. So it's a horizontal shift to the right by 2 units. So when I asked you to describe a transformation, this is the kind of language I'm going to be expecting you to write when I ask you to describe in words. Okay? Any questions on those 3? Okay, let's take a look at reflections. Okay, so reflections. That's this page here. And which function are we working with? What's our parent function here? What do we call our parent function here, someone other than Shane? Square root function, right. So it's an even root. So anytime I'm looking at an even root, I have to be careful of making sure my domain is defined. Now, our domain for the g of x equals the square root of x is what we say an implicit or an implied domain. It's implied. We know we can't take the square root of a negative number. So we know our domain here. If I asked you to represent the domain with interval notation, what would the domain be? Could someone explain the domain to me? The domain of G with interval notation? Bracket 0, comma, infinity, right. It's all non-negative numbers, 0 to infinity. Okay, that's the domain of G. Okay, so now we're going to be looking at what happens with these transformations. These types of transformations are called reflections. And they're basically a reflection across each of our axes. So we're going to reflect across the x-axis. We're going to reflect across the y-axis. So we have 2 equations. We have the opposite of our function. Or we have g of the opposite of x. So changing g of x to the opposite of g of x, is that an outside change or an inside change? Outside, because I'm still performing whatever my function says. I'm taking g of x, and then I'm changing the output to its opposite. So it's an outside change, and I'm changing the outputs. Okay. So how are the outputs of my parent function changed? How would you describe what happens to my outputs here? The outputs of my original function, the outputs of g of x, have what? Or you say it any way you want. How have the outputs of g of x changed when I put the little dash out in front? They have changed to the opposite. The outputs of g of x have changed to their opposite. Okay. So let's take a look at what this would look like on the graph. Okay, here's G. Okay. So which one, am I doing the red one or the blue one? I can't remember. Am I doing the red one or the blue one? Red. I'm affecting the I'm outside the function. Here's my transformation, that little dash, and it's outside my original function. So there I am. There's my transformation. All of my y values, which were above the y-axis, excuse me, the x-axis, have now changed to being below the x-axis. So 1 has changed to -1. Okay. 2 has changed to -2. 3 has changed to -3. 0 stays at 0. Okay. So this represents the function g of 1 equals the opposite of the square root of x. Okay, we call this a reflection. You can either use the word about or the word across. They're used equally well. You know, one book uses about, one book uses across. So about or across, I use them interchangeably. A reflection about or across the x-axis. Okay. All right. Okay, hang on. So make sure everybody catches up before you move along, Shane. Okay. Everybody got that? Okay. Okay, Shane, let's move on to where we're going now. To this one was where you were moving, right?
I think so, yeah.
All right. So now we've got our original function g of x, and now we're making x its opposite. Is this an inside change or an outside change? Inside. Are we changing the inputs or the outputs? How have the inputs changed? They've changed to their opposite. So now we're going to be graphing what? Our new graph, our transformation looks like this. Y equals the square root of the opposite of x. Does anybody have a problem with that? What's your domain here? What's the domain? Excuse me? Right. We can't keep our original domain. Our original domain was 0 non-negative numbers. If I put a 2 in here, I can't take the square root of -2. So my domain has to be changed in order to evaluate this function. The domain now, so when I look at its graph, the domain is not going to be on the right-hand side of my y-axis. The domain is from -infinity to 0. X must be a negative number or 0. So when I take its opposite, I have a positive number underneath. So let's go back to that. Where are we? Got to find it. There we are. So now let's do that. There we are. So you can see g of 2, which is a transform function. Here's the domain from -infinity to 0. And we are a reflection across the y-axis. So when we change the input, we are a reflection across the y-axis. So a reflection across the y-axis. Okay. So I hope on your papers you're doing like little diagrams of what we have here. All right. So that's reflections. So now I'd like you to go to your activity. And I'd like you to do G, H, and I. Label it and describe it. Okay, so again, you want to label some key points on your graph. You know, you can pick whatever points those are. Since you're changing the y values here on G to their opposite, you want to pick some y values that actually, oops, I got this point labeled incorrectly. This is 0, -2. You want to have some y values that you can actually change to their opposite. So G says take all my y values and change to their opposite. So this point is going to be transformed to be 0, positive 2. So I look on my graphs that I haven't picked already for a 0, 2 point. I've got one here in this first graph, there's 0, 2. And I've got one here in this graph. So it has to be either one of those two graphs, right? Okay, so I've got it narrowed down to 2 graphs. Now this point, negative 3, positive 1 becomes negative 3, negative 1. Oops, negative 3, negative 1, negative 3. All right, so we now know if we check that this is G. So this is a reflection across the x-axis. That's my description of the transformation. H says, flip me or reflect me across my y-axis. So that means this point 3, 1 becomes negative 3, 1. This point 0, negative 2 stays there. So then you want to start picking on some other points. 2, 0 is going to become negative 2, 0. So you should be seeing a straight line that has a negative slope, because this has a positive slope. This is a piecewise function. So this positive slope line will become a negative slope line, and you should expect your little crook on the other side. Should be 3, 1 where you have your peak on the other side. So you look down, and this is exactly what's happening in this graph if you compare the points. So this is H, and this is a reflection across the y-axis. Okay. Now we have to flip it both ways, and that's right here, I. Okay. Okie doke. So let's move on now. Let's go back to our lecture notes to stretches and shrinks. Woohoo! We're going to stretch and shrink. All right. I wish I could stretch. All right. Except for yoga and stretching before you exercise. Okay. So what function are we acting on now? What's our parent function? What's our parent function? X squared. Okay, so let's see. Here we go. Here's x squared. And here's my transformation of my parent function is going to have some number operating on the outside now, not as an add-in, not something I add or subtract, but now as a multiplier, as a factor. So when the number on the outside is 1, it looks exactly the same as its parent function. So now think about increasing this number to 2 or 3 or 4. What's going to happen to your graph? That's what we're about to investigate. So here we go. Here's the graph of j of x. It's going to now look like 2 times x squared. Okay, 2 times x squared. So am I acting on the inside of my function or the outside of my function? Outside, because the 2's on the outside. Okay. I've already performed my function j. It says square my input and then multiply it by 2. So we are changing the outputs or the y values only of my parent function. My x values are staying exactly in the same spot, and now I'm expecting something to happen to my outputs. How are these outputs changing? What's happening to my outputs? They're growing smaller or bigger? Bigger by what factor or what multiplier or what scale, or however you want to say it? 2, right? So because they're getting bigger, they're stretching. They're vertically stretching. Oh, stretching up. They're still being anchored at the same x values. They're being anchored at 0, 1, 2, 3, and all the numbers in between. Negative infinity, they're being anchored right there, but instead of going to their usual y spots, they're being stretched up. They're being vertically stretched up by a factor you could use, multiplier of 2. You don't use the word units anymore. Units are reserved for moving, shifting. So think about this x squared, and now all your y values are going to get to where they're going a lot quicker. Okay, so let's see if you can imagine what that looks like once I change this to 2. So here we go. Here we go. Okay, so there you see that this function for exactly the same. So at 1, I used to be at at 1, and now at 1, I'm at what? 2. So here I am at the same, anchored at the same place. I'm much bigger. I'm further from the x-axis. I've gotten taller. So some people think of this as narrower. Some people think of it as taller. I like to think about my y values rising, increasing much quicker than they were on the original. It's rising more quickly. Okay, this graph is rising more quickly than the parent function. So this function is being stretched when it's a positive number, vertically stretched on the outside. Okay, well, if I change that to a -2, it's going to have the same shape as that red thing, but what would it look like if I have -2 there? It's going to go, first it would do this, and then when I put a negative on there, what would happen to it? Austin, what's that? It would flip over the x-axis. So I'm not looking at reflections now. I want to now look at what happens to this thing when c is between 0 and 1, when it's a fraction. So let's take a look at that. Okay, so in GeoGebra, when we compare these two, how are they related? Well, the graph of 2 times j of x represents a vertical stretch of my original graph by a factor, or you could say multiplier if that's easier for you, multiplier of 2. Boom. It rises quicker, more quickly. Okay, so let's take a look at something other than 2. Let's take a look at a number that's between 0, when c is between 0 and 1. Can't be 1, because then it looks just like your parent function. Can't be 0, because then it would just be your horizontal axis, your x-axis. So let's see what happens when we make c a smaller number. Here we go. So here we are at 1. Now we're going to be a number between 0 and 1. So here we are at 1/2. Now look what's happened. We're further away from, you can either think of it as further away from the y-axis, or for each x value, your height is now closer to the x-axis. So before you went up quicker, now you're rising much more slowly. So as we change this to a number close and closer and closer to 0, that opens up and becomes wider, right? So let's see how we describe this. So if you have a number on the outside, it represents a vertical stretch or shrink of the graph by a factor of c. If c is greater than 1, we get a stretch. And when c is a fraction, we get a shrink. Okay? And it's considered a shrink because it's like taking this original parent function and squishing it, putting vertical pressure downward so that your vertical distances are half what they were in the original function. If you look at the table of values, your vertical distances, so like at -4, for example, when this was 1/2 x squared. Let's take a look at 1/2 x squared. Here we go. So if you put -2 in your original function, that would bring you to 4. -2 would bring you to 4. There you are. -2, 4 on your original function. On your new function, when you put -2 in, you're still 4, but then you take half of that, you get 2. So here you are. At -2, you're now 2. So you shrunk your vertical distance. This vertical distance originally was 4 units above. Now you're only 2 units. So your vertical distance has shrunk by a factor of 1/2. Okay, by a factor of 1/2. Okay, so that's vertical. Again, it works how you think it works. If your number is big, you stretch, you get bigger, taller, faster. If your number is a fraction, you get wider, you're being vertically shrunk, you're getting more wide. Your vertical distances are not as tall as they were. So now we can expect something funky because now we're going to look at horizontal and vertical, horizontal stretches and shrinks. Counterintuitive. All right, so what function are we looking at now? Oh boy, we get to look at the step function. So that's this function right here. There's our step function. From 0 to 3, we're the constant function 3. And then from 3 to 6, we're a linear function with a slope of -1, -1x plus 6. That's the equation from 3 to 6. So we're a piecewise function. Now, we're working on the inside. Well, when C is 1, we're exactly the same as our parent function. So now what happens if I change this value inside to a number like 2 or 3 or 4? What happens to this function? So let's look at the domain of this parent function. What's the domain of K? What's the domain of K? I start where and end where? Where do I start? What values of x do I start with, and what values of x do I end with for K? 0 to 6, including, right? So now we're going to look at the domain of K1 when C is a number like this, 2 times x. So if you're thinking of this as like a time function and a speed function, it's like, or some people might say, again, you can use that little trick I told you. What would I have to do to 2x to get back to x, to get back to my original x? What would I have to do? What do you have to do to 2x to get 1x? Divide by 2 or take half of it. So here's the number, here's C. You either divide by 2 or multiply by 1 over 2, which is a half. So either divide by 2 or multiply by 1 over 2, whatever that number is in front of x. All right. So you're getting there. What this means is when you double x, you're getting there twice as fast. You're getting to all your y values twice as fast. So let's take a look at what happens to our function when c becomes 2. There you go. There's our transform function. What's the domain now? Instead of 0 to 6, what's the new domain? 0 to 3, right? So the entire function happens in half of the time because all your x's, all your inputs have been accelerated. They've been doubled. So the entire function happens in half of the interval, half of the domain. Okay? Does that make sense? When you see it. So let's see. What if I move this up to 3? What should my domain be if I move C up to 3? The whole function will happen between what values? 0 to 2. So let's see. Getting closer and closer to 3. Here we go. Now my entire function happens between 0 and 2 because I've cut it by a third. It's going 3 times faster. 3 times faster. Okay. So again, counterintuitive. So if we change k of x to k of 2x, we're on the inside of our parent function. We're changing our inputs, and our inputs are being doubled. Our inputs are being doubled. Okay, and if you ever want to know how to put a step function into GeoGebra, here's how you do it. K of x equals, and then you have to use this if clause. If x is less than 3 and greater than or equal to 0, that's our first piece on our domain, then our function is defined to be 3, comma, if x is less than or equal to 6, greater than or equal to 3, then this is how we define our function, negative 1x plus 6. So when we graph these on the same set of axes, how are the two related? The graph of k times 2 of x represents a horizontal shrink by a factor of 1/2. You take whatever this number is and you put it as 1 over that number. So 1/2, because 1/2 of 2x brings you back to x. It shrunk, so when you shrink, your factor has to be a number between 0 and 1. It has to be a fraction if you're shrinking. Okay, so what happens if we now look at, for example, k times 1/2 x? Or with our slider, it's going to be this, 0.5x. So now my numbers, my domain is happening at a slower rate, right? So what do we think? All of our x's are being cut in half before we apply the function. So it's going to take me twice as long to get to where I want to go. So let's go down to 1/2. There we are. And now look at the domain. Okay, so now let's call this k sub 2 is, let's call this k sub 2 over here. And what's the domain of k sub 2? It's twice the distance. It's 0 to 12. It took twice as long to get there because all your x's were cut in half. So before I could even apply my function value to say what my output was, I was cut in half. So to get back to where I was, to get back to be a 1 or 2 or a 3, I had to put in a number that was twice as big, just the opposite, the inverse. So the graph of y equals kc of x represents a horizontal stretch or shrink of my original graph k of x by a factor of, be careful, what goes in here? Whether you're stretching or sinks, what goes in here? 1 over c, right? 1 over c. It's the inverse of whatever the number is, the multiplicative inverse. So if the number is 2, it's half. It's shrinking by half. If the number's 3, it's shrinking by 1 over 3. If the number's 1/2, it's increasing or stretching by 1 divided by 1/2, which is the reciprocal of 1/2, which is double, 2. So when c is greater than 1, we get a shrink. And when c is a fraction, we get a stretch. So now go to your activity and try, I think the only numbers left, you help me? What are the numbers left? Let's, D, E, and F, right. D is what we call a multiple transformation because you're doing 2 shifts here, and E and F are some type of stretch or shrink. So when you get that done, let me know, and you're free to go, and I'll see you on Friday.